Development cycles stall when accessing real patient data. Anonymization techniques like k-anonymity fail rapidly in high-dimensional electronic health record datasets, leaving system analysts unable to iterate quickly. The objective is generating statistically equivalent data that maintains the complex correlations necessary for training predictive models, while providing quantifiable privacy guarantees. We must move beyond simple masking or shuffling, which destroys feature relationships. The solution requires a generative model capable of learning the underlying joint probability distribution of the entire dataset. This approach ensures that the synthetic output reflects the real-world patient population demographics and clinical pathways, crucial for reliable application development and testing. For complex tabular data containing mixed types, continuous, ordinal, and categorical, the Conditional Tabular Generative Adversarial Network, or CTGAN, is the optimal architecture. Standard generative adversarial networks struggle with non-image data structures. CTGAN addresses this by employing a mode-specific normalization technique and a conditional vector mechanism. The conditional vector allows the generator to focus on specific subsets of the data during training, effectively handling highly imbalanced categorical features, such as rare disease codes. We utilize the Wasserstein loss function combined with a gradient penalty, known as WGAN-GP, to stabilize the training process and prevent mode collapse, a common failure point in generative adversarial networks when dealing with diverse patient attributes. Effective preprocessing is mandatory before feeding patient data into the CTGAN architecture. Continuous features such as laboratory results or age require normalization, typically using min-max scaling or z-score standardization. Highly skewed numerical features such as patient length of stay or total charges must undergo a log transformation to approximate a Gaussian distribution, improving model convergence. Categorical features, especially high-cardinality fields like ICD-10 procedure codes, cannot be simply one-hot encoded due to dimensionality explosion. Instead, we implement frequency encoding or entity embedding to reduce the feature space while preserving relational information, ensuring the generator learns meaningful representations without overfitting to sparse categories. The CTGAN training configuration requires precise tuning. Set the batch size relative to the total number of records. A batch size of 512 is standard for datasets exceeding 1 million rows. The generator and discriminator learning rates should be set low, typically 1 × 10 to the power of -4, using the autumn optimizer. Crucially, the number of training iterations must be sufficient for convergence, often exceeding 50,000 steps. Monitor the discriminator loss. It should fluctuate but remain stable, indicating the generator is effectively challenging the discriminator. If the discriminator loss drops to near zero and stays there, mode collapse is imminent, requiring adjustment of the learning rate or the gradient penalty weight. To achieve regulatory compliance, we integrate differential privacy directly into the training loop. This is implemented by applying the Gaussian mechanism to the gradients of the discriminator during the backpropagation step. Define the privacy budget using epsilon and delta parameters. Epsilon quantifies the maximum information leakage, typically set between 1 and 10 for practical utility. Delta represents the probability of privacy failure, usually set to a very small value, such as 1 × 10 to the power of -5. The noise scale applied to the gradients is inversely proportional to the desired epsilon. Higher noise ensures stronger privacy but reduces the statistical utility of the generated data, requiring careful trade-off analysis.
Statistical fidelity confirms that the synthetic data preserves the statistical properties of the real data. For continuous features, we use the two-sample Kolmogorov-Smirnov test to compare the cumulative distribution functions. A high p-value indicates that the distributions are statistically indistinguishable. For categorical features, compare the marginal distributions using the Jensen-Shannon divergence metric. A divergence score close to 0 confirms high fidelity. Furthermore, visualize the pairwise correlation matrix between features in both datasets. The synthetic correlation matrix must visually mirror the real data matrix, ensuring complex dependencies, such as the correlation between diagnosis codes and prescribed medications, are accurately replicated. Fidelity alone is insufficient. The synthetic data must prove its utility for machine learning tasks. Train a reference classification model, such as a gradient boosting machine predicting patient readmission risk, using only the real data. Then train an identical model using only the synthetic data. Compare the performance metrics, specifically the area under the curve score and the F1 score. The synthetic model's area under the curve score should be within 5% of the real data model score. If the utility gap exceeds this threshold, the generative model requires retraining with reduced differential privacy noise or increased training epochs. Privacy validation requires testing against known attack vectors. Membership inference attacks attempt to determine if a specific patient record from the original training set was used to generate the synthetic dataset. Implement a shadow model approach, where multiple generative models are trained on overlapping subsets of the real data. Compare the prediction confidence scores of the synthetic records against the real records. Calculate the nearest neighbor distance ratio, the ratio of the distance between a synthetic record and its nearest neighbor in the training set versus its nearest neighbor outside the training set. A high ratio confirms strong privacy protection. Handling longitudinal patient data, such as sequences of hospital visits or vital sign measurements over time, requires moving beyond static tabular models. For sequential generation, transition to architectures like CTGAN or recurrent generative adversarial networks. These models incorporate recurrent neural networks, specifically gated recurrent units, to capture temporal dependencies. Structure the input data as three-dimensional tensors, samples, time steps, and features. The generator must learn the transition probabilities between consecutive time steps, ensuring clinically plausible sequences of events, such as the progression from initial diagnosis to subsequent treatment interventions. Deploy the trained generative model as a microservice for on-demand data generation. Containerize the entire pipeline, including the model weights and necessary preprocessing logic, using Docker. Implement a RESTful API endpoint that accepts schema parameters, such as the desired number of records and specific feature constraints. The service should return the generated synthetic data as a JSON payload or a comma-separated values file stream. Integrate monitoring tools to track generation latency and resource utilization, ensuring the service can handle peak demand from development and testing environments without performance degradation. This architecture enables rapid, compliant data provisioning across the organization.